What do the 1980s puzzle classic Tetris and this linear system have in common? Well, not much, really. But that won't stop me from helping you understand how to solve a linear system using elimination, using Tetris as a visual metaphor. At this point, you understand how to solve a linear system using substitution, and it truly is as easy as just putting something into something else. So why introduce a more complex strategy than that? Substitution is great when you have a system like this, where X or Y are easy to isolate, or in this case, already isolated. But in a linear system like this, X or Y aren't as easy to solve for without time-consuming algebra and errors if you aren't careful. So instead of trying to fit a square peg into a round hole, you're here to learn how elimination can be used to solve this problem. And that's where the wonderful game of Tetris comes in. As a kid of the 90s, yes, I know, old, I spent hours of my childhood eliminating row after row after row in Tetris. Now, in case you happen to have lived under a tetromino for the last 40 years, am I actually almost 40? The whole idea behind Tetris is that you want to create a complete horizontal row to eliminate it from the screen. And therein lies the connection to our studies of linear systems. Rather than rearranging a line from this system to solve for y and substituting it into the other equation to solve for x, we're going to do something kind of random and kind of scary. Take a good hard look at the coefficients in this system. If you look close enough, you'll see that the coefficient on x is doubled in this line compared to this line. So the random scary thing we're going to do is we're going to multiply this whole line by 2. But why? Remember that this doesn't break math or anything because you did it on both sides of the equation. And when we do that, you will see that the coefficients on x are now equal. So why did we do this, and what does this have to do with Tetris, huh? Oh, right, math video. Well, since these two terms now match up, if we were to subtract straight down, we can eliminate them from the game. System. We continue to subtract straight down for the remaining terms in the system as well, and with our x term eliminated, we can very easily solve for y by dividing both sides of this equation by 9 to get y equals 4. So y equals 4 is half of our point of intersection. To find x, we can substitute our y equals 4 back into either line from our system. Doing a bit of algebra work will allow us to solve for an x value of x equals 1. So the point 1, 4 is the solution to our linear system. Okay, so that works. But wait, remember how we just randomly multiplied by 2 to get rid of x? What happens if we chose to eliminate y instead? Well, just like in Tetris, sometimes there's more than one piece that can eliminate a row. Well, the same thing goes for this system. You'll see that the coefficient on y in this line is 7 times the coefficient on y in this line. And so if we multiply this line by 7, our y terms are almost identical. But instead of subtracting, we now have to add to cancel our terms because 7y plus negative 7y will cancel them out. Adding straight down for the rest of the system will allow us to proceed in the same way as before. Dividing both sides by 45 will give us the same x equals 1. And subbing in x equals 1 into either line will give us our familiar y-coordinate of 4. Alright, so we played some Tetris and we solved a linear system using elimination. But if you want to truly master this strategy, you're going to want to head over to this video right here so I can show you all the stuff about elimination that confuses students. You're not going to be one of them.